Have you ever felt like exams are just this black box? You've done the revision, you know your stuff, but you're just not sure how to translate that knowledge into actual marks. Well, in this explainer, we're going to pry that box wide open. We're going to take an insider's look at a real GCSE physics paper and decode it, just like an examiner would.
So let's get right to it. What are examiners actually looking for? I'll give you a clue. Knowing all the physics equations is a fantastic start, but believe it or not, that's only half the battle. The other half? It's all about communication, and you guessed it, playing by the rules of the game. And that right there is the big secret. Success in any exam isn't just about what's in your head. It's about how well you can show it when the pressure's on. You see, the key to unlocking those top marks is understanding the rulebook that examiners have to follow. Think of it like the instruction manual for the exam itself.
All right, let's dive into that rulebook, the mark scheme. Now, this isn't some top secret document. It's the exact guide every single examiner uses to mark your paper. We're going to break down its most important rules, because knowing these can completely change how you tackle the exam.
First up, let's talk formatting. If you see a word in bold or underlined in a mark scheme, that's not for decoration, it's a direct command. A bold "and" literally means the examiner cannot give you the mark unless you've included both ideas it connects. And an underlined word, that keyword is absolutely non-negotiable. If you miss it, you miss the mark. Simple as that. Now for some really good news. Errors carried forward, or ECF. This is basically a lifeline in those long, multi-step calculations. So if you make a little slip up early on, you can still get marks for the next steps as long as you use your wrong answer correctly. What's the big takeaway here? You have to show you're working, always. Okay, this one is so important. Listen up. If a question asks you for, say, 2 examples, and you give 3, 2 that are spot on and 1 that's wrong, you could end up with 0 marks for that question. The rule is right plus wrong equals wrong, which means a single mistake can actually cancel out a correct answer. The lesson here, if they ask for 2, give them your best 2, and then stop. And finally, for those big, beefy 6-mark questions, examiners use something called level of response marking. Here, they aren't just ticking off keywords from a list. No, they're looking at the overall quality and the logical flow of your answer. It's all about whether you can build a coherent scientific story. Let's see how this actually works in our first case study. So, our first case study is a real classic, the describe an experiment question. This is all about laying out your steps in a clear, logical order, kind of like you're writing a recipe for another scientist to follow. Okay, here's the challenge. The paper shows you a graph from a light refraction experiment, and it asks you to describe how you'd collect that data. Now, this is a 6-marker, which means it's one of those level of response questions. The examiner is looking for a method that's clear, logical, and would actually work if you did it in a lab. Now, this slide shows what the mark scheme calls indicative content. Basically, the key ingredients for a top-level answer. But it's not just a rigid checklist. Notice the flow. It's logical. You set up, you shine the light, you mark its path, you measure, and then you repeat. It's that clear, step-by-step structure that gets you into that top level and bags you all 6 marks. Okay, let's switch gears and look at calculations. Now, you might think structure is less important here, but you'd be wrong. You need to show the examiner every single step of your thinking, because every line you write down could be another mark in the bag. Our second case study involves this baby walker, and the questions are all about calculating things like force and moments. Now, these are pretty standard formula-based questions, but they're hiding some classic traps that catch people out all the time. Just look at how a 3-mark calculation is broken down. You get a mark just for stating the right equation. You get another mark for putting the numbers in the right places, and you get the final mark for the answer with its units. This means that even if you mess up the math on your calculator, you can still walk away with 2/3 of the marks just by showing your method. And here it is, that classic trap I was talking about, unit conversions. The question gives you a distance in centimeters, but the equation needs it in meters. Forgetting to convert is one of the easiest ways to lose a mark. But remember, errors carried forward? Even if you forget, you can still get marks for the rest of your calculation if you do it correctly. So after converting our centimeters to meters and multiplying it by the force, we get our final answer, 0.15 Newton meters. You see how all those little pieces, the equation, the substitution, that crucial conversion, and the final answer all come together to get you the full 3 marks? All right, our final case study is all about explaining the why. In physics, it's very rarely enough to just state a fact. You've got to be able to connect it back to the science behind it. So this question gives us the light spectra from the sun in two different galaxies. See how those black lines have shifted to the side? The question is, what does that tell us? You've got to think like a detective here. The diagram has all the clues you need to solve the case. And here's how you build that perfect 3-mark argument. Point 1, the observation. You see the lines have shifted towards the red end of the spectrum. That's redshift, which means the galaxies are moving away. Point 2, the comparison. Galaxy A's shift is way bigger than Galaxy B's. And point 3, the conclusion. A bigger redshift means a faster speed. It's a perfect chain of logic.
Okay, so after peeking inside the examiner's rulebook and running through our case studies, what are the key strategies we've learned? Let's pull everything together into your ultimate exam toolkit.
And here it is, your 5-point checklist for exam success. Number 1, show all you're working. Let that error carried forward be your safety net. 2, structure those long answers with a clear, logical flow. 3, keep an eye out for those crucial keywords. 4, never, ever add extra answers to a list. And 5, always double-check and convert your units. Nailing these 5 things can make a massive difference.
So you see, an exam isn't really something to be afraid of. It's just a puzzle with a very specific set of rules. And now that you know those rules, you're not just a student taking a test anymore. You're a code cracker, and you're ready to solve it and show them exactly what you know. Good luck.